This is part 7 of the integration topic. Last time we looked at exponential functions, and in this video we're going to look at logarithmic functions. First, let's look at deriving y equals ln of x. Now you've seen previously that the derivative of ln of x is the hyperbola function, 1 on x. This means that if we go the other way and we integrate the 1 on x function, we get ln of x. Well, almost. We actually get ln of the absolute value of x, and then we have our constant of integration. Now, while you may have seen the reasoning for this before, if you'd like to refresh your memory, there's a really good video from Eddie Wu, which I'll provide a link for. So click on the link provided to go and have a look at a video that he does explaining why we get the absolute value signs. Alrighty, let's start writing this out nice and neatly, and we'll add in a few examples as well. So starting with our standard hyperbola, 1 on x, when we integrate this function, we get the natural log of the absolute value of x, plus our constant of integration. And let's also note that in this case x cannot be equal to 0, because x is on the denominator here in this fraction. Let's also note that in previous videos we talked about polynomial functions, so these ones, x to the n, and we talked about n cannot be equal to -1. This is essentially what we're dealing with here. This is a case where we have the integral of x to the power of -1, because x to the power of -1 is just 1 on x. So we're now dealing with those here. Okay, and in the previous videos we said we would look at these, but they're a separate type of integration. Well, here they are. Now, as well as the standard hyperbola, 1 on x, we can also look at integrating functions of the form f-x over fx. So this is, for all intents and purposes, the chain rule version when we're dealing with logarithms. So if you notice an integral where we have some function of x on the bottom of a fraction, and then the derivative of that function of x on the top of the fraction, this is equal to the natural log of the absolute value of that function of x that is on the bottom of the fraction. Okay, then we also have our constant of integration, and in this case this entire function of x that's on the bottom cannot be equal to 0. So let's now do two examples. We'll do one example that fits in with what we wrote up here, and we'll do one example that fits in with this type of question. Number 1. Evaluate the integral of 3 on x dx. Now this is a definite integral between 5 and 1. Notice that this doesn't quite match up with the 1 on x that we were talking about before. It's very close. It's just 3 lots of 1 on x. So what we might do is bring that constant 3 out the front of our integral, and then we are left with 1 on x after the integral sign. Now that we have the integral of 1 on x, we can apply the natural log of f of x. So we still have our 3 out the front. Now we can apply the natural log of x, sorry, not f of x, natural log of x. And we have our upper bound and our lower bound. And what we'll do now is apply the fundamental theorem of calculus. So let's sub in x equals 5. Now the absolute value of 5 is just 5. Okay, so we'll just write ln 5 minus, and the same with ln of 1. Right, the absolute value of 1 is just 1. Now, while ln of 5 will give us some sort of decimal number, ln of 1 is just 0. So when we calculate this, or if you just think about what the log graph looks like, you get 0. And so, keeping this answer exact, 3 lots of ln 5 is our answer for this integral. On to example 2. Find the exact value of the integral. Okay, now we've got x plus 1 on the top over x squared plus 2x plus 4. And once again, this is a definite integral. So the first thing we need to do when we look at an integral like this is say, okay, it's a fraction, and what I've got on the bottom is a quadratic, right? Highest power is 2, and what I've got on the top is a linear function. So this should give us a clue. The fact that the degree of the polynomial on top is 1 and the degree on the bottom is 2, this lets us know that, hey, maybe we're looking at a log function here. So let's just focus on the function of x on the bottom. Let's call that f of x. So we've got x squared plus 2x plus 4. And let's see what the derivative of this is. So what is the derivative of x squared plus 2x plus 4? X squared becomes 2x, the plus 2x becomes plus 2, and the 4 disappears. So our 2x plus 2 is the derivative, and that's not what we have here. But do you see a link between x plus 1 and 2x plus 2? What happens if we factorize by bringing out 2? We get 2 lots of x plus 1. And so now we can see that the only difference between what's on our numerator in the initial question and what we have here is this constant value of 2. That means we can very easily make our question look like this, which is what we want. So let's rewrite our initial question. Our initial integral would be really great if it looked like this. However, we can't just go and multiply something by 2, as that changes the question. So if we multiply by 2, we are also going to multiply by a half, and we'll have that half out the front of the integral. So what we've just written is actually the same as our original question, but we now have it in the form of f dash x on the top and fx on the bottom, which means we can use the rule that we wrote previously. Evaluating this integral gives us the natural log of the absolute value of this function of x on the bottom. So x squared plus 2x plus 4. And so now all that's left to do is to evaluate this function by substituting in 3 and 0. When we substitute in 3, we will get the natural log of, let's do this mentally, so we have 3 squared is 9, plus 2 lots of 3, so that's 9 plus 6, which takes us up to 15, plus another 4. Now, like we saw in the last example, the absolute value of a positive number is just that number. So let's write ln of 19. And we're going to subtract what we get when we substitute in 0. This is a little bit easier. We get 0, 0, plus 4. So we're going to subtract ln 4. Now this question has asked for the exact value. So what are we going to do now? Let's give ourselves a bit more room. Well, when we have one log take away another log, and we're dealing with the same base as we are in this case, this is the natural log, we can use a rule that says we combine those log functions into one, and we use division. So this is one of our log laws. And so when we look at this answer, there's not much more we could do to simplify it. We could mess around with it a little bit by maybe applying another log law and taking this half out the front and putting it as a power, but that is subjective as to whether it makes it simpler or not. So we're just going to leave our answer as it is. Looks pretty good. It's in exact form, and that finishes off our second example. Great work.